So in this session, we'll discuss about RS codes, Reed-Solomon codes based on the scientist names. So to understand Reed-Solomon codes, there is a need to refer BCH codes and its extensions. Okay, and here RS codes are the special case of BCH codes. So that's why first let me revise the notation for the BCH codes. Okay, and later on, okay, and how can you develop the coding for RS codes? Okay, and we know that according to the BCH coding, that is based on Galois field 2. Galois field 2. So the set of elements are 0, 1. Galois field 2 with the base 2. Okay, but the encoding that is based on extension field GF of 2 power m. The elements are 0, 1, alpha, alpha square up to alpha power 2 power m minus 2. So for example, if m is equal to 4, now the set of elements becomes 0, 1, alpha, alpha square, it is alpha power 14. All these are the parameters related to the BCH coding. Now for BCH coding, conjugate roots. So this notation is required for finding the minimum polynomial, and the conjugate roots are beta square, because 2 is a element or base element. After that, beta 2 square, which is nothing but beta power 4, and beta power 2 cube, which is nothing but beta power 8. So simply I will write the same thing as beta square, beta power 4, beta power 8, like that. Okay, and here for m is equal to 4. Okay, and here we have to find the minimum polynomials for different values, different primitive elements. So for example, okay, and here I am doing all these calculations for m is equal to 4 only. So for m is equal to 4, if alpha is the element, alpha is a primitive element, then the conjugate roots are, just we have to substitute beta by alpha square, alpha power 4, alpha power 8. Because alpha square is there, then I will take another example. If alpha cube is primitive element, then the elements are, that means you have to replace beta by alpha cube. The elements are alpha cube whole square, alpha cube whole power 4, alpha cube whole power 8. So the elements are simplified: alpha cube, alpha power 6, alpha power 12, alpha power 24. And we know that alpha power 24 is nothing but alpha power 9, or the set of elements are alpha cube, alpha 6, alpha power 9, alpha power 12. That's what we have done for BCH coding. Okay, and here this is the procedure as far as the representations are concerned. Okay, now once we got the idea about a BCH coding with the base 2, now the extension for this is Q-ary BCH coding. Or Q number BCH coding. So that means here the base element is GF of, there's a Galois field of Q, and Q may be one of the element, like it's a 2 square or 2 cube or 2 power 4. You can take any value, but Q, now base element is a Q, and the elements are 0, 1, alpha square up to alpha power q minus 2. Okay, and for example, for assuming q is equal to 16, then Galois field of 16 directly. Now the base is 16, straight away I can take. Now the elements are 0, 1, alpha up to alpha power 14, and it is same method of maybe GF of 2 power 4, but Q-ary BCH coding, that is assumed, that is represented with the GF of Q like this. And similar to the BCH coding or Galois field, here also there is an extension field GF of Q power M, and the elements are 0, 1, alpha, alpha square up to alpha power Q power M minus 2. That's the representation. So here we are comparing BCH coding with Galois field base 2 and Galois field of Q. And once we got this representation, now we have to think about conjugate roots, similar to the previous case, conjugate roots. So now the conjugate roots are, earlier is a beta, beta square, beta 2 power 2, because 2 is the base. Now the conjugate roots are beta, beta power q, beta power q square, beta power q cube, like this. And in this case, in the Q-ary BCH coding, minimum polynomial that can be calculated as phi of x. It is a multiples of pi I is equal to 0 to e minus 1 x minus beta power q power I. Okay, and here with the example we'll get more clarity on this. Minimum polynomial is calculated in this format, but in the BCH coding with the Galois field base 2, we have calculated phi 1 of x, phi 3 of x, phi 5 of x, we have taken the LCM, but because Q value is very high, it is quite difficult to do all this calculation. That's why minimum polynomial is will be calculated in this format. And the parameters as far as the Q-ary BCH coding are block length. Block length is n, that is equal to q power m minus 1. Parity check, n minus k less than or equal to 2mt, and minimum distance d minimum greater than or equal to 2t plus 1. Okay, for example, if m is equal to 2, sorry, and for q is equal to 2, it is like a BCH coding as we discussed. Okay, and for other extensions also we'll discuss about this one. Okay, now in the Q BCH coding, Q-ary BCH coding, it is based on G Galois field Q power M, and in that if M is equal to 1, it is referred as RS code, Reed-Solomon code. That is a base for the Reed-Solomon code. And the parameters are in this RS code. The parameters are block length. Now m is equal to 1, and the parameters are block length, n is equal to q minus 1. Earlier I mentioned n is equal to q power m minus 1. M is equal to 1. Thus n is equal to q minus 1. Parity check. Parity check. N minus k less than or equal to 2mt. Or because m value is 1, it is equivalent to n minus k less than or equal to 2t. And dimension, k is equal to, actually it is n minus 2t, or it is equal to q minus 1 minus 2t. Minimum distance, d minimum is equal to 2t plus 1. For example, if you are taken, if q is equal to 16, the reason for taking q is equal to 16, because in the BCH coding and all these things we are taking the example gf of 2 power m and m is equal to 4, which is nothing but gf of 16. So that's why I'm taking q is equal to 16. If q is equal to 16, now the parameters are n is equal to 15, and k, that is the parameter required, k is equal to 15 minus 2t. So based on the t means the number of error corrections will decide. If t is equal to 3, for example, that means triple error correcting, then k is equal to 15 minus 6, that is 9. So in this case 15 comma 9 RS code for triple error correcting. Q is equal to 16, N is equal to 15, corresponding K value is 15 minus 2t, if T is equal to 3, okay, and K value is 9. So number of message bits are 9, 15 comma 9 RS code. It is a notation for RS coding. Okay, after getting the dimension 15 comma 9 RS code, now we have to start with this. For example, if alpha be the primitive element in the GF of Q, generate a polynomial, because encoding means generate a polynomial G of X of T error correction. So T error means we have to take the elements alpha square up to alpha power 2t. Now for any element like alpha or alpha square, alpha power I, if that is the element in the GF of Q, then its minimum polynomial phi I of x is equal to x minus alpha power I. Even though I have taken minus, okay, and because it's the XOR operation, there is no negative element, that will calculate A, will treat as x plus alpha power I. And in this alpha power I representation, so for example, if I taken alpha is an element, then minimum polynomial is phi I of x is equal to x minus alpha or x plus alpha. If alpha square is a primitive element, then phi of x is equal to xi minus alpha square or x plus alpha square, like that. Okay, and here we'll take minimum polynomials. Okay, now we'll discuss one example related to RS coding, and here I will assume Q is equal to 16, that is GF of 16, that is based on that we are trying to represent RS code. So another parameter required to discuss the example is how many errors we are trying to correct. So let us assume P is equal to 3, that's a triple error correcting with Q is equal to 16. We are trying to find RS code. Okay, now to find this representation, there is a need to refer generator polynomial G of x. So now generator polynomial G of x is calculated from the primitive elements alpha square, alpha cube up to alpha power 6, because according to our representation it is up to alpha power 2t. So here we have to take the representation. Now the polynomial corresponding to alpha, that is phi 1 of alpha is equal to x minus alpha or x plus alpha. So like that, here we have to take phi 2 of alpha is equal to x minus alpha square or x plus alpha square in the XOR operation or in the modulo 2, phi 3 of x minus alpha cube. So here there is no equivalent representations on all the things like BCH coding, because Q is equal to 16 is a base element. That's why for every element you have to calculate the same parameters. Phi 4 of x, it is x minus alpha 4, phi of x is equal to x minus alpha power 5, phi 6 of x, that is x minus alpha power 6. Now generator polynomial G of x is simply represented as, it is a multiplication of x plus alpha into x plus alpha square, x plus alpha cube, x plus alpha power 4, x plus alpha power 5, x plus alpha power 6. The generator polynomial that can be simplified by, so now the polynomial for triple error correction G of x is equal to x plus alpha square plus x plus alpha cube plus x plus alpha power 4 plus x plus alpha power 5 into x plus alpha power 6. For example, if it's a double error correcting, generator polynomial that can be calculated up to the factor alpha power 4 only. Okay, now for calculations, okay, and for verification purpose, so here I'm giving the simplification also. In the first step, first two terms are formed one factor, third, fourth terms like this, and later on it may be simplified. So here for simplification of all these terms Like in the first factor, we got alpha square plus alpha. So here I referred Galois field table, x square plus alpha power 5 x plus alpha cube. Okay, and here this is a presentation, a short simplification. So here you can practice the same thing, and here we'll get the representations. So here I multiplied first two factors, third and fourth factor, and fourth and fifth factors. After that I got the terms three factors like this. Three factors like this. So like the first two factors multiplication, third and fourth factors multiplication, and fifth and sixth factors multiplication. And further, first two factor again first two factors, if you are multiplied first two factors, the resultant is like this, and the resultant is represented like this, and here it is multiplied with the last factor, and finally I got the representation in this way. Equations, I have referred this table. So here also I have taken the generator polynomial, and here the equivalence for this. For example, alpha power 4 is 1 plus alpha, alpha power 5 is alpha plus alpha square, alpha power 6 is alpha square plus alpha cube. So here I used all these. Now the generator polynomial that can be represented or simplified as x power 6 plus alpha 9 plus alpha power 13 x power 5 plus alpha power 11 plus alpha power 22 plus alpha power 6 x power 4 plus alpha power 24 plus alpha power 15 plus alpha power 10 x cube plus alpha power 17 plus alpha power 10 plus alpha power 12 x square plus alpha power 14 plus alpha power 19 x plus alpha power 21. Now these terms simplified by, so for x square actually the coefficient is alpha power 17 plus alpha power 10 plus alpha power 12. That can be simplified as, according to the table, alpha power 17 is nothing but alpha square, because alpha power 15 is 1. Now alpha power 17 is represented as alpha square, and alpha power 10 is 1 plus alpha square plus alpha power 12. Alpha power 12 is nothing but alpha square plus alpha cube. Now it can be simplified as alpha power 6. Similarly, for the factor for the coefficient of x cube, it is alpha power 24 plus alpha power 15 plus alpha cube. That can be simplified as alpha power 24 is nothing but alpha power 9. It can be obtained by alpha power 24 is represented as alpha power 15 into alpha power 9. Alpha power 15 is 1. So now you can easily simplify the same thing. Plus alpha power 15 is 1 alpha cube. It can be simplified as alpha power 4. For x power 4, here I followed the notation like this. The coefficient for alpha power x power 4 is alpha power 11 alpha power plus alpha power 22 plus alpha power 6. Alpha power 22 may be represented as alpha power 7. Now it is alpha power 11 plus alpha power 7 plus alpha power 6. With the table, okay, it can be simplified as 1 plus alpha cube, which is nothing but alpha power 14. For x power 5, the factor is alpha power 9 plus alpha power 13. And by substituting the equivalence for alpha power 9 and alpha power 13, we'll get the simplification 1 plus alpha square, which is nothing but alpha power 10. Similarly, for the coefficient x, it is alpha power 14 plus alpha power 19. Now, alpha power 19 may be replaced or simplified as alpha power 4. And finally, we got alpha power 9. With all these simplifications, now the generator polynomial that can be represented as g of x is equal to x power 6 plus alpha power 10 x power 5 plus alpha power 14 x power 4 plus alpha power 4 x cube plus alpha power 4 x square plus alpha power 6 x plus alpha power 6. And once we got the generator polynomial, then it is very easy to get the code word. Code word is nothing but data d of x multiplied by g of x. D of x is the data polynomial, g of x is the generator polynomial. This is the encoding for RS coding. So here we are assuming the q value. Based on that, actually the extension field is gf of q power m, but we are taking m is equal to 1. That is a RS coding, encoding.